So in this video, we're learning about Avogadro's law. Avogadro's law is all about volume and the number of moles of a gas you have in a space. That little symbol in the middle there means proportional to, and so what this law is saying is that the volume in liters of your gas is directly proportional to the number of moles in your gas. So in other words, as the number of moles goes up, the volume will go up if your temperature and pressure remain the same. Or as the number of moles of your gas goes down, the volume will go down. Those things are directly proportional to each other. That means that they move together. As one goes up, the other goes up. As one goes down, the other goes down. So how can we turn that into a law that we can actually do math with? Well, the technique that we've used so far with all of our gas laws is this. We turn our proportionality, that volume is proportional to number of moles, into an equal sign with a constant. You can pick any constant you like there. I'm just going to use K. So I know that volume is equal to any old constant multiplied by the number of moles. I don't need to have a number for that constant. I just need to know that it's a constant thing. Then what I'm going to do is rearrange this for K. So to do that, I'm going to need to divide both sides by n, right? Divide both sides by the number of moles. That will cancel n out. And so I will get volume divided by number of moles is equal to this constant K. Now, why would that be interesting? Well, it's because I can look at the initial and the final conditions. The initial conditions of my gas are going to be some V1, some initial volume, divided by some N1, some initial number of molecules. That will equal my constant K. And the final conditions will be some volume V2, divided by my N2, the final number of moles, the final volume. That will equal the same constant K. The key trick here is that if both of those things equal K, then they must equal each other. We can't write it like that, so we'll write it like this. V1 over N1 will equal V2 over N2, and that right there is Avogadro's law. Let's see an example of this. So let's say you have a sealed container. It's got a volume of 350 milliliters and a mass of 1.2 grams. Now for any of these problems, and this is going to be especially important when we get to the ideal gas law soon, we're going to be converting these volumes into liters. So let's convert that to liters right now. The mass of the empty container is 1.2 grams, but when you fill it with oxygen gas, it has a mass of 3.23 grams. The first thing we're asked is just how many moles of oxygen gas are even in this container? And this is not super obvious because we're not told directly the mass of oxygen gas, but we can figure it out. Right? We know the mass of the container plus the oxygen, and we know the mass of the empty container. So if I subtract those two things, I should get the mass of the oxygen gas inside. So the mass of the oxygen gas will be the mass of the container filled with oxygen minus the mass of the empty container. This is essentially what your weigh scale does when you zero it or tare it with some container on it and then add some substance to your container. So that's the mass of oxygen gas I have here. The molar mass of oxygen gas is going to be 2, because there's 2 O's in every O2 situation, times the molar mass of a single oxygen, which is 16, or 32 grams per mole. Then I can find the number of moles just by doing mass over molar mass. So my number of moles of oxygen gas is going to be that 2.03 grams divided by 32 grams per mole, my molar mass. And that gives me around 0.0643 moles. So that is my number of moles of oxygen. But if I want to go a little bit further, now let's imagine I want to keep the same temperature and pressure, and imagine how many moles of oxygen gas could I now fit into an 100 milliliter container. Well, this is where Avogadro's law will come in. So I'll write down the things I know. In my initial container, I had 0.0643 moles of oxygen gas. That's my N1, my initial moles. In my original container, I had a volume of 350 milliliters, and we're converting that to liters, so 0.350 liters. In my final container, I have a volume of 100 milliliters, or 0.100 liters. What I'm trying to solve for here is N2. So that's my required thing. I'm trying to find the number of moles that would fit. Now, this fraction is set up not very nicely, so there's a few different ways I can deal with it. I'll show you one nice algebra technique that I like. It's called cross multiply and divide. So I'm going to multiply these guys, and that will equal those guys multiplied. So you can do this whenever you have a fraction equals a single fraction. Cross multiply and divide is a great technique to have. So v1 times n2, so that's these guys, will equal v2 times n1. That's these guys here. And then I need to solve this for n2, so you just need to divide by the v1. That's the divide part of cross multiply and divide. That cancels out my v1, and I get n2 is equal to the final volume, which is 0.1, multiplied by the initial moles, 0.0643, and divided by the initial volume, 0.350. I'll plug that into my calculator here. 0.1 times 0.0643 divided by 0.350, and I get a final number of moles of 0.018. And it looks like for significant figures I should probably stop there. Moles. So just a little sanity check to make sure here. This is a smaller container and it fits fewer moles. So that makes sense and is a logical thing here.